Similarly to how Nicholas Copernicus presented the heliocentric model, another dazzling correction of how we might interpret the universe could arise, starting a discussion known as the emergence of cosmology. This emergence is set apart by critical disparities in our estimations and comprehension of the universe's crucial properties, such as its age, size, and pace of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has stopped this discussion with a picture that resists material science. So, what precisely is this emergency, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of a misrepresentation. It's more similar to a survey that has been in progress. The emergency refers to a place where how we might interpret the universe is challenged, especially in terms of its age and size, which are connected by an extensive safety buffer. The presentation of the JWST has been pivotal in this setting. For this advancement, we were limited in how far we could see into the early universe. However, with the JWST's further developed abilities, space experts can investigate considerably more distant worlds, giving us new viewpoints on the universe and testing a portion of our past conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical information that can either support or challenge our current models of the universe. To understand the emergency in detail, looking into the view is significant. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model, has been exceptionally successful in making sense of various elements of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It includes components like dark matter, which applies gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each groundbreaking observation, particularly with instruments as cutting-edge as the JWST, raises the possibility that our current model might be inadequate or need to be updated. The lambda CDM model makes explicit predictions about the attributes and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the far-off past should be smaller, less evolved, and contain fewer heavy elements compared to those we see in the nearby universe. This is because heavier elements are formed in the centers of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the movements within groups and clusters of galaxies, as well as the properties of the cosmic microwave background, CMB. As we travel back into the past, according to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at astronomical distances greater than our own. This would lead us to expect to enter times of the universe without apparent stars or galaxies. However, researchers have found contradictory evidence that challenges these expectations, resulting in an emergency in cosmology. The emergency in cosmology centers on the uncertainty about the age of the universe. Different estimation strategies give various outcomes, leading cosmologists to struggle to accommodate these disparities. To attempt to address this issue, researchers use several techniques to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, to determine the expansion rate and, thus, the age of the universe at different times. The CMB, a remnant radiation from the early days of the universe, is a key tool for this calculation. Detailed maps of the CMB, like those provided by the European Space Agency's Planck mission, offer important information about the composition of the universe. However, these maps lack data on dark energy, a significant component of the current universe. Despite this limitation, researchers can use the Friedmann equations along with other observations to estimate the expansion rate of the universe at different times and eventually determine its age. Another approach to determining the age of the universe involves observing exploding stars, specifically Type 1 supernovae. These supernovae act as standard candles, since they have a known intrinsic brightness. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance and, therefore, the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential to cosmological calculations. It is particularly useful for determining the Hubble constant, a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang, about 13.8 billion years ago. It has been observed that the universe has been expanding consistently. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, perhaps dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy speeding up the universe's growth. In January 2018, researchers found something interesting. Although some telescopes showed that the expansion rate of the universe changed depending on the place of observation, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant parts of the universe. This discrepancy in measurement highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Now, considering the expansion of the universe independently of your local region, you would observe the same phenomenon at the same speed as the Hubble expansion rate. Initial calculations were based on limited data. However, with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Different telescopes use readings of the CMB to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which limits our view of the universe. Since the discovery of dark energy in the 20th century, researchers have been stumped by the inconsistencies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more accurate, smaller variations arise, driven by the development of more advanced systems. This progress, however, raises more questions than it provides definitive answers. Although the differences are minor, with just 10 to 20 million years separating the estimates, given that the universe is around 13.77 billion years old, it still warrants careful examination. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most accurate measurements, it has been extensively tested since its launch in 2009 for validating its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may fluctuate over time and be linked to dark energy or some other unknown factor. This possibility has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Settling this uncertainty in supernova models could help resolve the disparity in measurements. This emergency in cosmology has been further exacerbated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding requires a complete update. However, the problem is that we have no idea where to begin to comprehend the extent of the scientific revolution. Let's take a look at the origins of the universe around 50 million years after the Big Bang. Stars, black holes, and star clusters began to emerge, potentially even as soon as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much more distant and, therefore, older than the standard cosmological model predicts. This disparity suggests that our model needs a major update. The discovery that the expanding universe relied on galaxies is a major development. JWST images show galaxies that formed much sooner than anticipated by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This changed the universe into a soup of hydrogen atoms, with some helium and residual background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, slowly pulling them together to lead to the first stars. These early stars, made mostly of helium and hydrogen, engaged in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen, but as time went on, the gas became enriched with heavier elements produced in the cores of stars. This process led to the formation of galaxies that contained not just hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential for life. The emergence of new discoveries, particularly those from the JWST, suggests that galaxy formation could have occurred much earlier than we thought, challenging our current understanding of cosmology. These galaxies are seen as they were just 100 million years after the Big Bang, and their existence raises questions about how quickly the first stars and galaxies could form and what mechanisms were at play. The discoveries of the JWST indicate that the universe might have experienced an even more rapid and complex early evolution than previously thought. Shaking the foundations of the lambda CDM model, the recent discoveries made by the James Webb Space Telescope, JWST, have added more depth and complexity to our understanding of the universe, accelerating cosmological emergency discussed by scientists. The JWST's images and data have revealed galaxies that exist at much greater distances, and thus are much older, than the lambda cold dark matter, lambda CDM, model anticipated. These findings suggest that galaxies began forming much earlier than previously thought, perhaps as soon as a few 100 million years after the Big Bang. This could mean that the rate of galaxy formation was much faster in the early universe, challenging the idea that galaxy formation was a slow process that took billions of years. One of the key findings that the JWST has revealed is the presence of mature galaxies in the very early universe. According to conventional models, the formation of these galaxies should have taken longer, with more primitive structures appearing first. The existence of galaxies that are not only fully formed but also showing signs of significant evolution within a few 100 million years after the Big Bang complicates our view of cosmic history. If these galaxies are indeed this evolved, it suggests that the processes that led to galaxy formation and growth were much more rapid than previously expected, pushing back the timeline for the formation of complex structures. This discovery could have several implications for our understanding of the early universe. One possibility is that the conditions needed for galaxy formation, such as the cooling of gas and the collapse of dark matter halos, were more favorable than we thought. Early stars and black holes could have played a much larger role in accelerating the development of galaxies, possibly by triggering rapid star formation through processes like radiation feedback or the formation of supermassive black holes at the centers of early galaxies. This rapid formation of galaxies could have happened much earlier than anticipated, challenging our understanding of the interplay between dark matter, dark energy, and ordinary matter in the shaping of large-scale structures in the universe. Furthermore, the JWST's ability to observe galaxies in the cosmic dawn, a period about 100 to 400 million years after the Big Bang, has begun to reveal that the first galaxies might have formed and started evolving far earlier than the lambda CDM model predicts. The detection of light from these galaxies could potentially push back the timeline for the formation of the first stars, which were thought to appear around 200 million years after the Big Bang. This could also have profound implications for our understanding of reionization, the process that made the universe transparent to light by ionizing hydrogen atoms. Since this process was thought to occur over a relatively extended period, the discovery of galaxies forming so early might suggest that reionization happened much faster than expected, possibly indicating that the early universe had a different composition or set of conditions than we assumed. The contradictions between what the JWST is revealing and what the lambda CDM model predicts are also stirring the debate over the nature of dark matter and dark energy. These two components of the universe, which make up the vast majority of its mass-energy content, remain elusive, and their properties are not fully understood. The discrepancies observed in galaxy formation and evolution could be indicative of some unknown interactions between dark matter, dark energy, and normal matter, suggesting that the current cosmological model might need to be adjusted or replaced. Moreover, the study of early galaxies is also pushing the boundaries of our understanding of stellar evolution and the role of the first stars in the cosmos. These first stars, called population 3 stars, were thought to be massive, hot, and short-lived, playing a crucial role in the formation of the first heavy elements and the subsequent evolution of galaxies. However, the JWST has the potential to provide direct evidence of these stars and offer insights into their formation and impact on their environments. If these early stars were as common as the JWST's data suggests, it could mean that we need to reconsider the timeline and mechanisms of star formation. As these discoveries continue to challenge the existing models, cosmologists are faced with the possibility of a major shift in our understanding of the universe's formation and evolution. The findings from the JWST are undoubtedly reshaping the foundations of cosmology, forcing researchers to rethink our theories of the Big Bang, galaxy formation, and the role of dark matter and dark energy. In light of this, the field of cosmology is entering a new era, where the mysteries of the universe are becoming even more profound, and the models we have long relied upon may no longer be adequate to explain the complexities of the cosmos. This cosmological emergency highlights the dynamic and evolving nature of science, where new discoveries continuously challenge our previous assumptions, ultimately leading to a deeper understanding of the universe we inhabit.